because it's just a pain in the ass. But okay, so I'm going to prove two theorems. These are probably the two most interesting and important theorems in R. So there's the Archimedean principle, and I'm going to misspell Archimedes, I'm sure. Archimedean principle. This says if you have two elements of R, and one of them is positive, let's say x is positive, then there exists an integer that's also positive, such that nx is bigger than y. And I'll explain what these two things mean. And then the other one, don't know if it has a name. Oh yeah, sure, I'm going to call it, it has a name, but you guys aren't going to understand it. Density of Q. So we call this the density of the rationals. We're going to know what the word dense means by the end of next week, I think. But here we show if x and y are in R, and x is not y, there exists a rational number q such that q is strictly between x and y. So the word, we'll eventually say the word q is dense in R. As in, like, no matter how hard you try, there's always a q between any two numbers. Does that make sense? Yeah?
Sorry, is A, the way it's stated, is it complete, or should it say x is less than y?
Doesn't matter. It doesn't matter. The point is, I mean, because the number, I didn't say the integer couldn't be 1. Right? If x is bigger than y, you just let n equal 1. The point is saying no matter what number you take, nx will eventually be bigger than it. If you just take higher multiples of it. I mean, you're right that for it to be meaningful, it'd be nice for x to be less than y. But it doesn't matter. It doesn't affect the statement. Does that make sense? So the reason, but this is an extremely important thing. I don't know if anybody's ever heard of the hyperreals. I doubt it. But there's this idea. So somebody tried to do this whole class, this analysis class, in something called non-standard analysis, by studying reals that also have these really minute little things called infinitesimals, which are numbers that no matter how many multiples of it you take, they don't get bigger than 1. These really small things like dx, like when you look at the derivative dx, dy, dx is an infinitesimal and dy is an infinitesimal. So you're taking the quotient of, I mean, it's this really messed up like set theoretic way of trying to do it. The only advantages I see is like proving the chain rules, like cancellation and stuff like this, but it's otherwise a gigantic mess. But the thing is, this is an extremely important property. This says two numbers are comparable, and eventually I add a number to itself enough times, it's bigger than any other number. A positive number, and if, obviously if it's a negative number, it's less than any other number. Make sense? I mean, it's an important property. I know it seems obvious, but I'm just going to prove it to you really quickly. Great, so now I have to prove this. So let me ask you this, guys. How do you think I'll prove something like this? There's going to be a contradiction argument here. The reason there's going to be a contradiction argument is because, like, assuming that you, I mean, it's really hard to show you can do this. It's a lot easier to assume you can't. Okay? So we're going to prove part A, proof for part A by contradiction. Assume there exists y in R such that nx is less than y for all positive integers n. Okay? So every integer, no matter which positive integer, I'm assuming that this y is so big that nx will never reach it. Or x is greater than 0. Okay, so what does that tell me about this set, guys? It has an upper bound, or is bounded above. Again, this is how all these arguments are going to go. All right? Does that make sense? That means this is bounded above. Now we're in R now. So now life is good. So we're going to let alpha be the supremum of E. Of course, E is not empty, right? Because it has X. Certainly. Okay? But so we're going to let alpha be the supremum of E. Now I'm going to come up with a contradiction. So here's the big trick, and I mean, I didn't quite emphasize it a lot in the previous thing, but remember, the trick with the supremum is usually you find something that's not the supremum, and you conclude something about it. So here's the thing I'm going to conclude. So if alpha is the supremum of E, what can you say about alpha minus x? Well, x is positive, so this is smaller than alpha. So this is smaller than alpha, so alpha minus x is not. This is what I mean by, you usually use it in the negative, the supremum. Is not, let's just say supremum of E. So what does that mean? So there exists M in, let's say, Z, such that mx is greater than alpha minus x. Again, this is not the supremum because it's less than the supremum. So that means it's not an upper bound. Yes? Alpha minus x is not the supremum, so it's not an upper bound. So there's something in this set, in here, such that this is bigger than alpha minus x. Right? Here we go, here's the magic. So I move the x over here. So m plus 1 x is bigger than alpha, because I just added x to both sides. Contradiction. Alpha cannot be an upper bound. Yeah? But do you guys see what we're getting at there? It's a very simple trick, and this is literally how, I mean, I'm telling you, I'll try to, I'm not sure there's one on this homework, but I'll try to put them on, especially once we're doing sequences. There's a lot of proofs that the trick with the supremum is you take something less than the supremum and say, this is not the supremum. And that's how, and that's all we did. We didn't do anything magical. This is just basic definitions. Make sense? Crazy. I'm going to prove part B, but I'm going to prove part B kind of, well, maybe, I don't know. Do you guys want all the details? All the details are in the book. Or do you want me just to explain what the proof is doing? I'll try to do both. It's just, this is a tricky proof because it doesn't look like it's doing what it's supposed to be doing. So right, part B is kind of fun, okay. So part B basically says I take two numbers that are not the same. Or let's change this up. I'm just going to change this to make it easier. It doesn't really make a difference. We knew one of these was true anyway. Let's just assume x is less than y. All right. If x is less than y, I'm going to prove to you that there's a p between them. All right. Sorry, the way I wrote it before was wrong. But so if x is less than y, since x is less than y, we know y minus x is positive. Right? So let's pretend I said here are two numbers, prove to me there's a rational between them. What would you try to do? So let me maybe draw a real line somewhere over there. And I'll try to explain the idea of the proof. But the point is I give you two real numbers. Right, so this is x, this is y. How am I going to try to find a rational between them? Well, the general idea is this. You figure out how far apart these guys are. Right, there's some number apart. And then you take a number n such that 1 over n is smaller. Right, so let's say these guys are 2/5 apart. Then I might take, I don't know, 1 over 10. 1 over 10 is less than 2/5. Now I'm just going to look at all the multiples of 1 over 10 until I get in here. Because I know when I get in here, I can't go all the way across because this is more than 1 over 10, so that's going to be in here. Does that make sense? But so eventually it might be like 500,000 over 10. But it'll eventually get stuck between x and y. And that's actually what the proof's going to do. It's just because Bruden's an ass, he does it in some confusing way that doesn't look like that's what he's doing. So the very first thing Bruden says is, by A, we know there exists n such that n times y minus x is greater than 1. Right? That's the first thing. This is the first thing he says. I'm literally doing Bruden's proof. I'm just trying to explain to you why this makes sense. What is this really saying? It's saying we know there's an n such that 1 over n is less than the distance between y and x. You see? If I divide by 1 over n, now suddenly 1 over n is less than the distance between y over x. Y minus x. Does that make sense? So we're first going to find an increment that we're sure has to eventually land in here if we take a high enough multiple. And then he's like, oh, now he's going to do all this black magic, which is basically saying, I'm going to find you the number that's going to get us in there. But let me show you what the black magic looks like. Well, he realizes this can be